Hi, George Diamond here. Now today we're going to be looking at some examples of the first derivative test, using the first derivative test to locate relative maximum and minimums on an open interval on a graph. Now, in our textbook, again, this is section 3.3. Okay, the first derivative test, this is video number 2. Now, video number 1, we talked about the first derivative test. We really didn't use it any, but we talked about increasing and decreasing functions. And then we kind of introduced and talked about the first derivative test. But in this video, we're going to look at some actual examples. Now, to begin though, we're going to try our first problem. Now, the first problem, we're going to look at how to tell whether or not a graph is increasing or decreasing. Right. So it says find the intervals on which f of x is increasing or decreasing. Now, our function here, erase this. Our function of f of x is equal to, this is x cubed minus 3 has x squared. Right, so this is our function. Now remember we said in our first video now, the derivative tells us whether a graph is increasing or decreasing. If the derivative is positive, the graph is increasing from left to right. If the derivative is negative, it's decreasing from left to right. So we're going to figure out what the derivative is, and then we're going to figure out a way to tell whether the graph is increasing or decreasing on a particular part of the graph. So to start off, we're going to find the critical numbers of our graph. So the critical numbers, a possible maximum or minimum point, or maybe a place where the derivative doesn't exist. So to start off, let's get our derivative first. Now the derivative, this is a little cubic polynomial, so the derivative will be 3x squared minus 3x. So this is our derivative. All right, so to start off, first thing I want to do is let's see if we can find the critical numbers. The critical numbers. Now, critical numbers are where the derivative is equal to 0 and where the derivative does not exist. So where the derivative is equal to 0 and where it doesn't exist. Now I'm going to take my example down here. I think you've got the information already. Just a little bit more room to work. Now, first thing you notice about your derivative, the derivative is a polynomial. So the derivative is defined everywhere. So there are no places where the derivative doesn't exist. All right, so we simply have to worry about finding the zeros of the derivative now to get our critical numbers. So let's set the derivative equals 0. So it'll be 3x squared minus 3x. We'll set this equal to 0. Now we're going to put it in factored form and then solve this equation. Now, looking at our derivative here, you have a greatest common factor of 3x, so we're going to factor 3x off this binomial. You factor 3x off the first term gives us x minus 1 remaining inside our parentheses. Now to get our critical numbers, you have to take each of these polynomial factors and set them equal to 0. So do 3x equals 0, x minus 1 equals 0, so x equals 1, and x equals 0. So we have two critical numbers at 0 and 1. So on an open interval, a possible relative maximum or minimum. Now, in this problem, all we need to do is determine what are the intervals where the graph is increasing or decreasing. Now, to check that, we have to check the first derivative. Now, what I'm going to do here, we're going to set up, rather than trying to do the entire graph, we're going to set up a little number line graph, I guess, sort of like this right here. A little number line graph. Now, this is called a wiggle graph. Now, I have no idea why they call it a wiggle graph for, but this is what they call it. So what we're going to do is this little number line, all this little number line is going to do is going to kind of help us visualize what the graph is doing. All right, so to start off, let's put 0 and 1 on our number line. So just those two numbers. All right, so the rest of the numbers we're going to leave off. So 0 here and 1 here. Now, above our wiggle graph, we're going to put the derivative. Right, so what's the derivative doing? Is the derivative positive or negative? And kind of underneath it, I'm going to put f, the function. All right. Now, what we have to do with to tell whether the graph is increasing or decreasing and what intervals it's increasing or decreasing, so we've got to check the first derivative. Now, remember, the first derivative tells us whether the graph is increasing or decreasing or not. Now, the first interval from negative infinity to 0, what's the graph doing? Is the graph increasing or decreasing? Now, to tell, we got to see whether the derivative is positive or negative. Now, to do that, here's what we do. everywhere on the interval from negative infinity to 0, this curve should be either increasing or decreasing. Now, to tell which, we're going to pick out a test value. Okay, we're going to pick us out a test value of each interval. And we're going to test those numbers in the first derivative. So, how about we check from negative infinity to 0? Okay, let's try negative 1. Okay, let's see whether the graph, the curve of f would be increasing or decreasing at negative 1. All right, so let's take the negative 1, and we're going to substitute this into the first derivative. Now, don't substitute it back up into the original function. Now, that'll give you the y value. That's all that gives you. So we want to see whether it's increasing or decreasing. And for that, we have to use the derivative. So let's take this test value. Now, if the derivative is positive at negative 1, then it should be positive everywhere on that interval. If it's negative, then it should be, then the derivative should be negative everywhere on that interval, and the graph will be decreasing on the interval. So let's take the negative 1 and let's substitute it into the derivative. All right, so let's see what we get. So the derivative at negative 1 would be 3 times negative 1 squared minus 3 times negative 1. Okay, and let's see what we get as we check this derivative. Negative 1 squared would be 3 minus negative 3 would be plus 3 is 6. All right. So on the interval, so at negative 1, the derivative is positive 6. Now, all that really matters is whether the derivative is positive or negative. The 6 really don't matter. What counts is this is a positive 6. All right. The fact that it's 6, it could be 600, but if it's a positive 600, that means the derivative is positive and the function itself will be increasing. So this is going to be, so the derivative will be positive and the graph itself is increasing from negative infinity to 0. Okay, now let's try another interval. Okay, what about the interval from 0 to 1? Now this time let's pick us out another test interval this time, another test value. I want to try about 0.5. Let's try 0.5. Now, what's the derivative? What happens to the derivative at 0.5? Now remember, if the derivative is positive, the graph will be increasing. If it's negative, it's going to be decreasing. All right. So let's try the 0.5 in our derivative. So the derivative at 0.5 will give us 3 times 0.5 squared minus 3 times 0.5. Right, now I did this just to save us some time. We end up with, I've already done this beforehand, is negative 0.75. Now once again, the derivative is negative. Now, so the derivative is negative. That means the graph itself is decreasing. So the graph will be decreasing when x is 0.5. That means everywhere on that interval, from 0 to 1, the graph is going to be decreasing. Right. Now let's try the last interval down here. Now the last part of the graph goes from 1 to positive infinity. So let's pick us out a test value, about 2. So let's substitute 2 into the first derivative, and let's see if the graph is increasing or decreasing on that interval. So let's take the 2, plug it in. So the derivative of 2, it should be 3 times 2 squared minus 3 times 2. So we end up here with, what is this, 4 times 3 is 12 minus 6, which is positive 6 again. So on the interval from 1 to positive infinity, the graph is positive, and that means that the graph is increasing again. All right. Now let's make sure we've answered our question now. The question asks, okay, what are the intervals on which the graph is increasing and decreasing? So okay, let's do this increasing. It's going to be increasing. And where is the graph decreasing? All right, now to start, from negative infinity to 0, the graph is increasing. All right, so it would be from negative infinity to 0, and from 1 to positive infinity. Okay, let's see, where's the graph decreasing? Now the graph will be decreasing from 0 to 1, so from 0 to 1. So that's the intervals where the graph is increasing and decreasing. Now this isn't the first derivative test. This is just telling whether, identifying where the graph is increasing or decreasing. So remember now, whenever we decide, if we need to decide or determine whether a graph is increasing or decreasing, we use the derivative. It doesn't really matter so much what number the derivative is so much as whether the derivative is negative or positive, right? Because the sign tells us whether the graph is increasing or decreasing. All right, let's try another example here. So let's try another one. Get this erased. All right, so this time, let's try the actual first derivative test now. So let's try the first derivative test. Okay, so let me get this erased. There we go. Now, our second problem, let me get it set up here. Problem number 2. It says to use the first derivative test to locate all relative extrema. Right, this would be on an open interval. Right, so remember, it's not a closed interval. On a closed interval, you would have to check the endpoints, but this is an open interval. Right. Now, our function, f of x is equal to x cubed, okay, minus 12x minus 5. Right now, as I look at this problem, now I actually have my blue Pike Central hat here, so it looks pretty good. I didn't wear it the entire time, but here's my blue Pike Central hat. Also, I'm wearing my orange shirt today. Right, so this is one of my school colors. So I'm wearing my orange shirt. Okay. So to start off, I said we need to locate our critical numbers. We're going to do a wiggle graph, and then from there we can decide, whether we have any maximum or minimum and what they are. So any relative maximum, relative minimum. Right. So here's our function. Now start off, let's get our derivative. Now the derivative here will be 3x squared minus 12. Right, so we've got our derivative. Now to get our critical numbers, where is the derivative equal to 0? And where is the derivative does not exist? All right. Now, first thing you recognize, the derivative is a polynomial. There are no places where the derivative doesn't exist, so there are none. All right, so we'll talk about that. Let's set the derivative equals 0. So it'll be equal to 3x squared minus 12. Now we're going to have to factor this and solve this for x. This will be 0 equals, now I'm going to factor 3 off because it's x squared minus 4. And this will be 3 times x plus 2 times x minus 2. All right, so our critical numbers then would be x equal negative 2, x equal positive 2. So we have 2 critical numbers again. All right. Now we're going to decide now a possible minimum or maximum at each of those x values. All right. Now let me take this down. A little bit more room. So make sure we have enough room to do our wiggle graph. All right. So we start our number line graph, if you will. All right, so here we go. So we'll put negative 2 here and positive 2 here. All right. And now let's see, we're going to describe the derivative above the wiggle graph, and then we're going to describe the function itself below the wiggle graph. All right. So let's see, to get started, let's pick this out. Now, so we need to know what the graph is doing on each of these intervals. Now, you got 3 intervals. You got the interval from negative infinity to negative 2, then from negative 2 to positive 2, and then from positive 2 to positive infinity. So what's the graph doing on each of these intervals? Is it increasing or decreasing? And then from there we can decide whether we've got a relative minimum or a relative maximum now. Okay, now we've got our derivative. So the derivative is 3x squared minus 12. So let's pick us out a test value again. How about negative 3? So we'll try negative 3 for one test value. Okay, let's take the negative 3, plug it into our derivative for x. Let's see what we get. So the derivative at negative 3 will give us 3 times negative 3 squared minus 12. All right, so 3 times negative 3 squared minus 12. And let's see, what do we get here now? The negative 3 squared is 9, times 3 is 27. 27 minus 12 is what, 15? All right, so positive 15. Okay, now the number itself really doesn't matter so much as the fact that it's positive. Okay. Now, since it's positive, that means that the derivative is positive and the graph is increasing. Right, so from negative infinity to negative 2, we know that the graph is increasing. Now, so we don't know for sure what the graph looks like, especially, but you kind of have an idea. This is a cubic polynomial, so we have some idea. But we don't have to know exactly what the graph looks like right now, just to decide whether we have a maximum or minimum. Okay, let's pick us out another test value. How about 0? So we'll try 0. Substituting 0 into the original function, so into the derivative rather. Because remember now we want to see whether the derivative is increasing, whether the graph is increasing or decreasing. So take your test value, off that interval. And you can use any number you want. I'm just picking out the 0. So let's take the 0 and substitute it into the first derivative. Let's see what we get. So the derivative of 0 would be 3 times 0 squared minus 12, which is negative 12. All right, so the derivative is negative. So the derivative is negative, right? Okay, that tells us that the function itself is decreasing on the interval from negative 2 to 2. Okay, let's try one more. Let's try a test value of 3. So on our last interval. So from 2 to positive infinity, what's the graph doing? All right. Now, you got to be careful. A lot of students will see this pattern here. The graph is increasing, decreasing, and they'll automatically assume that the graph is increasing again. Now, you need to check a test value to make sure. Now that may work. That assumption may work on a lot of functions, but some functions it may not. You actually have to get a sign change. So the derivative has to change from positive to negative, negative to positive in order to have a maximum or minimum value. So you want to make sure that you actually do pick out a test value and check it in the derivative. We got the graph is increasing, decreasing. Now I would expect it to be increasing on the next interval, but we still got to check it in our derivative. So let's take the 3, plug it into our derivative here. So the derivative at 3 will give us 3 times 3 squared minus 12. Okay, which is 9 times 3, 27 minus 12, which is positive 15 again. So once again, the derivative is positive, just like we thought, and it's increasing from 2 to positive infinity. Okay, erase this right here. Okay, now first, let's describe where the graph is, the intervals where the graph is increasing and decreasing. So it would be increasing, and where is it decreasing? All right. Now the graph will be increasing from what, negative infinity to negative 2. Okay, and from 2 to positive infinity. And decreasing from negative 2 to positive 2. So this is a little cubic function. These are pretty easy to do, just little polynomials. Okay, now let's decide, let's answer the question. It says that the question says to locate all relative extrema. So that means maximum or minimum values. Now, let's notice what the graph is doing. From negative infinity to negative 2, the graph is increasing. Okay, now at negative 2, the graph starts to decrease now. So now the graph is going down. So we're talking about a relative maximum at x equal negative 2. Now, so the graph is decreasing, then at positive 2, the graph starts to increase again. Right? So the graph is decreasing, then it's increasing. Now we've got a relative minimum value. Right? So as we describe what the graph is, what's happening, whether the negative 2 is a relative minimum or a relative maximum. Okay, we've got a relative maximum at x equal 2, negative 2, and then a relative minimum at x equal positive 2. So relative maximum. Now to get the y values, you have to take each of these x values and substitute them back into the original function. Now, I'm not going to do that to kind of save some time on our video. But if you got to locate the actual point, the actual max or minimum, you have to substitute these back into your original function. Okay, let's try another problem. So this is a little cubic polynomial. These little polynomials are pretty easy to do for the most part. Okay, let's try one that's a little bit more difficult. Let's try a radical function. So let me get this erased. All right. So let's try this problem right here. This will be our third example and our last example. Okay, so here we go. Number 3. Now once again, we're going to locate all relative extrema. And our function this time, f of x is equal to, now this is a cubic polynomial, or a radical function. Now as I write it down, I'm going to convert it to rational exponent form. So this will be x squared minus 4 to the 2/3 power. So we're going to have to take the derivative, which means we're going to change it anyway. So we'll go ahead and as I write it down, we'll go ahead and convert it from radical notation, radical form to rational exponent form. So to get it started, let's go and get the derivative. Now this time, to do the derivative of this function, so to find the derivative, we're going to have to use the chain rule. Okay, so take the derivative of the outside, bring the 2/3 down. Okay, so take the derivative of the outside, leave the inside the way it is. Now you got to subtract 1 from your exponent, which gives us to the negative 1/3 power. So the derivative outside, leave the inside the way it is, times the derivative of the inside, which is 2x. Okay, now let's rewrite this back as a fraction. We don't want that negative exponent, it'll be a little bit easier to work with here. So the derivative will be 2 times 2x will go to the top of the fraction, so that'll be 4x over. Now on the bottom of the fraction we have 3 times x squared minus 4 to the positive 1/3 power. Okay, this is our derivative. Okay, now we got our derivative. Next, let's see if we can locate. Where the derivative is equal to 0. So we're going to get our critical numbers and where the derivative not exists. All right. Now I'm going to take the problem down. So if you need to, make sure you have the problem copied down. I got it up here still. So I'm going to kind of get this out of my way to give me a little bit more room. Okay. Now, to begin, where does the derivative not exist? Now, your derivative is a fraction. Remember, with a fraction, the denominator cannot be equal to 0. So to get where the derivative doesn't exist, let's take the 3 times x squared minus 4 to the 1/3 power and set just the denominator equal to 0. Okay. Now, let's divide both sides by 3. 3's will cancel. That gives x squared minus 4 to the 1/3 power equals 0. Now, to get rid of the 1/3 exponent here, let's cube both sides. So we'll cube that side. We're going to cube the 0. That gives us x squared minus 4 equals 0. That means x squared is equal to 4, x is equal to plus or minus 2. So 2 critical numbers, 2 and negative 2. All right, so 2 critical numbers. Now let's find where the derivative is equal to 0. Now this time you got to take the entire derivative and set the whole thing equal to 0 now. So we're going to do 4x over 3 times x squared minus 4 to the 1/3 power equals 0. Now to solve this for x, remember now, you're going to break your fraction up by multiplying the bottom of the fraction to both sides. So we're going to multiply the bottom here. That gives us 4x is equal to 0, or just x equals 0. All right. Now let's count them. We've got x equals 0, 1. X equal plus or minus 2, that's 3 critical numbers now. Now we want to see what's happening to the graph at each one of these critical numbers. Let's see with a relative maximum or a relative minimum. So let's start our wiggle graph up here. And let's see, we got -2, 0, and +2. So let's see what's happening here. So we'll do describe the derivative and then the function underneath the wiggle graph. Right now, so we set this up. So we're going to start off, let's see if we can pick this out at test value. Right off, now we got 1, 2, 3, 4 intervals that we have to check. So let's try a test value from each one. I want to erase this. We don't need this anymore. All right, so we got our critical numbers on our wiggle graph now. Okay, let's pick this out a test value. Let's try -3 first. Let's take the -3. Now we need to know whether the function or the graph is increasing or decreasing from -infinity to -2. So you want to take that -3, a test value, and substitute it into the derivative. Right? Now remember, don't put it back into the original function. You want to substitute it back into the derivative. The derivative tells us whether it's increasing or decreasing. So here's our derivative. So the derivative here would be the derivative at -3. And this would be 4 times -3 divided by 3 times -3 squared minus 4 to the 1/3 power. Now, to save a little bit of time, I've already got these calculated here. Okay, this will calculate out to -2.3. So -2.3. Now, if you have your calculator, you can just punch it up there on your calculator, make sure that you've got the same thing that I got. So once again, the derivative is negative. Okay, that means the graph itself is increasing from -infinity to -2. All right. Now let's try another test value. Let's try from -2 to 0. How about we try -1? Okay, let's see what the derivative is doing, what the graph is doing this time. So let's take the -1, substitute it into our derivative now. So it'll be the derivative at -1. And this will be 4 times -1 over 3 times -1 squared minus 4 to the 1/3 power. Now, once again, to save time, I've already calculated this. Now I got 0.9. Now, remember now, that's a positive 0.9. The only thing that really matters is that the number is positive. The number itself doesn't matter. So the number is positive, that tells us that the derivative is positive, and the graph, actually, let me change this now. So we have so this is positive, so the graph is going to be increasing. Now on the first interval, the derivative is negative, which means the graph was decreasing. All right, so let me make that change there. So just a little bit of a change. So it's going to be decreasing. And then from -2 to 0, the derivative is positive, so it's going to be increasing. All right, so I caught that. Okay, let's try another test value. So let's try, let's see, how about +1? All right, so we'll try +1. Now let's take the +1, plug it into our derivative now. So substitute it in. So the derivative of 1 would be 4 times 1 divided by 3 times 1 minus 1 squared minus 4 to the 1/3 power. All right, now, once again, I've done this calculation here. I ended up with -0.9 for our derivative. Now, so the derivative is negative at x equal 1 on the interval from 0 to 2. Now, remember, that means that the derivative will be negative everywhere on that interval, and the graph is going to be decreasing from 0 to 2. Now, let's do the last interval down here. Okay, how about we try +3 this time? Now, we would expect, now look what our graph has done so far. It's decreasing to the left of -2 and then increasing and decreasing. I would expect the graph to be increasing again. But you've got to check that value to make sure. You actually have to get a sign change before you have a maximum or minimum value. So let's take the 3, plug it in for x now, into our derivative. So the f prime at 3, this would be 4 times 3 divided by 3 times 3 squared minus 4 to the 1/3 power. Now, when I calculated this, I got +2.3. So +2.3. Okay. So that means the derivative is positive, just like we thought it would be, and the graph is going to be increasing. Now, to answer our question, okay, what are any relative minimum or maximum values on our curve? Now, notice what's happening. At -2, 0, and 2. Those are our 3 critical numbers. Now, each one of them is a possible minimum or maximum value. And we use our derivative now to tell which. Now, at -2, the graph is increasing and then decreasing. So, at -2, we're going to have a relative max. Now, at 0, now notice at 0, to the left of 0, the graph is, let's see, well, it's not right. So the graph is decreasing. Wait a minute. It's decreasing and then increasing, so it's decreasing down like so, and then increasing. So this would be a relative minimum, right? So I'm going blind, I think. This is it. So I'm glad I caught it. That's so good. Now at 0, the graph is increasing and then decreasing. So it's doing this, so it's increasing and then decreasing. So the graph is, so this would indicate a relative maximum value. So a maximum at x equals 0. And at 2, the graph is decreasing and then starts to increase again. So another relative minimum. So as you look at our graph, you're going to have a relative minimum value. So relative minimums, there's 2 of them at x equal -2 and x equal 2. So x equal -2 and x equal 2. And a relative maximum value, okay, at x equals 0. So relative minimums at -2 and 2, and a relative maximum value at x equals 0. All right. Okay, 3 examples. We've done a radical, we did a polynomial. So hopefully, if you can see how this goes. You're going to have to get your critical numbers again. Get your critical numbers. Put your critical numbers on a little number line graph. We call it a wiggle graph for some reason. I mean, nobody knows why. Pick out a test value from each interval. Check it in your derivative to see what the graph is doing. And remember now, if the derivative is negative, the graph is decreasing. If the derivative is positive, the graph is increasing. So remember now, the derivative tells us whether the graph is increasing or decreasing. And this is 3 examples. Hopefully they've helped.